Hey guys, Mr. B here, and in this video we're going to be going over the chapter 1.2 notes on using a scientific approach. So in this section we're going to be talking about the scientific method, how it works, how scientific laws are different from scientific theories, and there's a lot of vocab. So what is the goal of a scientific method? So pretty much in order to answer this question, we got to again think back about what is science and why do we do science. So a lot of times, of course, in order for us to gain information about the world, we're coming up with an organized plan to gather information and essentially communicate that information to other people once we are done with it. Okay? And all of this together is what we consider the scientific method. The main goal, however, to make sure we realize is that any scientific method, the goal of it is to solve a problem or better understand something that we didn't understand before. Okay? It's always the goal. So you can do science on something that you might not consider to be a scientific topic, but you can approach it scientifically, right? So like, for example, imagine that we are just going to make a paper airplane just because I feel like it, right? I'm bored in class. I'm just going to fold up some paper, make a paper airplane, just throw it across the room because why not? If we did that and I asked you, was that, thing you just made, was that scientific? Like, did you, like, folding your paper airplane, were you doing science there? You probably look at me and go, no, I just made a paper airplane. It's not sciencey. I wasn't like mixing chemicals or anything or doing an experiment. Okay. Could we make it scientific? Yeah. How so? Simple. All we do is we introduce a question and a problem that we're trying to solve. So, for example, rather than just making a paper airplane and just throwing it through the air, here's a question we could pose and go, what aspects of a paper airplane make it fly the furthest? So now, if we pose the question of what things about a paper airplane make it fly the farthest? Now when we make this paper airplane, we're trying to learn something. There's a problem that we're trying to solve. And now probably instead of just making a paper airplane and throwing it, we're probably going to make more than one. And every single time we make a new one, we're probably going to change something about it to do some testing. And all of a sudden we're doing all of these different iterations to try to learn some kind of information. And that, now what we're doing, that's science. Okay? So understand that, like, you guys do science on an everyday basis. You just don't think about it because it's just like natural to you. And that's normal. Okay? Anytime you do any kind of testing or experimenting or problem solving, you're doing science. All right. So when we do science, we make observations. In the last section, we talked about observations. Those can be things that we obtain with our senses. So seeing things, touching things, tasting things, smelling things, whatever. Repeatable observations are what we call facts. Okay, now this word facts is a word that is used very often in everyday language and stuff like that. And a lot of times people like to use it in the sense of it means something is true, right? So, oh, that's a fact. Therefore, that is like true. It's 100% true. In science, a fact is something that you can just observe you can observe it repeatedly, okay? So like, for example, it's a fact that the sun rises in the east and sets in the west. And it's not necessarily a true statement or anything. It's the fact that I can see that happen every single day, right? Every single day I can see that happen and I can observe it over and over. Therefore, it is a fact. It's a fact that if I pick something up off the ground and I let go of it, it will fall to the ground. That is a fact. Not because it's true, it's because I can do this over and over and over again and I can see the same result happen over and over. So like if people say like, oh, it's a fact that, aliens exist. That can be a fact if it's something that you can observe over and over again, but not always, right? So, if it's a fact that aliens exist, well, you can't repeatedly observe aliens. Therefore, it can't be a fact. So, understand that the word fact does not mean that something is true or not true. It just is a word we use to describe observations that we can see over and over again. Now, we do science a lot of times. We propose a hypothesis, which Basically, it's just we have an idea in our head about why something is, it does the thing that it does. But the main thing we need to understand is in order for our idea to be a good one, or our hypothesis to be a good one, it has to be testable. So like, for example, let's talk about Bigfoot, for example. I could propose like, oh, well, Bigfoot exists, but the only reason why no one's seen him yet is because he's really hard to find. Okay, well, can we test that idea? Can we test the idea that Bigfoot is hard to find? Sure, I guess. How could we do that? Well, we just go look for Bigfoot. Okay, for how long? Well, until we find him. Okay, and what happens if you never find him? Well, we just keep on looking. What, forever? Eventually you have to stop, right? Like, you can't just go forever. And so that's a hypothesis that's actually not testable. You might think it's testable. So you go, well, we just keep on looking, right, until we find him. But there's no end. If there's no end to it, then you can't test it, right? Because it just goes on forever. So there has to be limits to how you test something. So understand that all hypotheses are not testable. Even though they might seem like they are at first, they're not. So that's a really important thing to understand. Now, when we test a hypothesis, of course, we perform experiments. Sometimes these experiments can be very complicated, and other times they're very simple. In experiments, we have variables. Okay, variables are things that we typically change during an experiment. The variables that we ourselves usually are changing are called manipulated variables. Then there's the variable, of course, that we are hoping is going to respond to the changes we're making. So if we change one thing and then we do a measurement seeing, okay, if I change this, does this happen? That's what we call a responding variable. Okay. So in the example of like the paper airplane thing I gave you before, our manipulated variables would be like, if we have wider wings or narrower wings, or we tilt the wings up or tilt the wings down, those are all manipulated variables. And the responding variable would be how far the plane goes, right? So we can measure the distance. And then, of course, the last thing we have are controlled variables, which are actually on the next slide, or the next two slides, somewhere in here. But controlled variables are variables that we don't change, that stay the same throughout the whole experiment and always are staying the same. Because then we know that when we're doing our experiment, the results we're seeing are only from the things we're changing and not these other things, okay? So it's very important that when we do experiments, we do controlled experiments, which are everything stays the same, you only change one aspect, and then you measure to see if that aspect, that variable, caused any kind of difference. So while the responding variable is what we measure, the manipulated variable is what we're changing, a controlled variable is something that we don't change, okay? It stays the same the whole time. Last thing then is what happens when we do an experiment and our data does not support the initial idea we had to begin with, right? Our hypothesis. Well, do we just change our data and fudge the numbers to make it work? No. A lot of times what we have to do is we have to revise our initial idea, right? Or propose a new one. Understand that experiments are constantly being revised all the time. Like, you're not always going to get the results you want to see in the first time. Sometimes it takes you 2, 3, 4, 5 experiments. Sometimes it takes you thousands or millions of experiments to get the results that you want. And every single time you got to change your hypothesis. That's just how it goes. Okay. It's part of doing science. Once we've done enough of these tests and we've actually seen the results we're looking for. So we see the results we're looking for, and we can repeat this experiment over and over and over. We can keep seeing the same results every time. At this point, we can start to develop what we call a theory. Okay. Now, the word theory is also another word that is used commonly in our everyday language that doesn't really mean what we think it means. So when we use the word theory in our everyday language, a lot of times people use it in the sense of like, ooh, it's a good idea. Like, ooh, I have a theory about blah, 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 which really is saying I have an idea about blah, 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 right? That's not what the word theory means. That's the word hypothesis. A hypothesis is an idea, whether it's a good idea or a bad idea, right? A well-educated or a well-detailed idea or a bad one, it's still a hypothesis. A theory is not an idea, okay? It's not a guess. It's not a really educated guess. It's not a really, really good idea that just hasn't been tested yet. That's not what a theory is. A theory is something that has already been tested many, 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 many times. And the theory now is an explanation for why we are getting the results we're getting based on the observations that we're seeing. That's a theory. The only way for you to make a theory is to go, no, this has been tested on multiple times by lots of different people, and the results are always the same. So a theory is basically just an explanation, if that makes it easier to remember. A theory is an explanation. It's not a guess. It's not something that just hasn't been tested enough yet. No, it's an explanation about something that's already been tested plenty of times and can be explained because we know how it works. So understand that we're not trying to prove theories. Okay, theories are not things we prove because they're not guesses. They're not ideas. We prove hypotheses. We don't prove theories. Theories are just explanations that can become stronger when more facts continue to support them. Okay? And if an existing theory fails to explain new things, so like let's say for example we have a theory about paper airplanes and how they work, but then all of a sudden we make a paper airplane and we try it out and it all of a sudden doesn't go that far. Even though we did all the things we were supposed to, it doesn't work the way that it should be. We have to now take the theory that we used to have, get rid of it, do a bunch of more experiments, and eventually come up with a new theory that then explains why that, experiment we just didn't work the way it should have. So theories are oftentimes gotten rid of and replaced or revised when things happen that contradict them. Now, there are practice problems in this video. We're not going to go over them because there's a video of me going over those separately, so go watch that one. We'll talk about the last part here, or the last kind of bit of stuff, and that is scientific laws and how they're different from theories. Okay, so a scientific law is not like a theory. Okay, a theory is an explanation about how something works based on lots of tests, and a law is really just telling you what's going to happen, but not explaining why it's going to happen. Okay, so here's the main difference. Scientific theory explains to you this is why something happens. And a scientific law tells you this is what's going to happen. But I'm not going to tell you why this is happening. Just this is what's going to happen. Okay, so like for example, let's talk about the theory of gravity and the law of gravity. The theory of gravity will explain what gravity is. Oh, it's a force that is attractive. It's an attractive force between two large masses, and whenever they come close to each other, you get poles and blah blah blah, and the larger the object is, the more gravity it has, and blah 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 blah. The law of gravity will basically say two objects attract each other. But why? I don't care. I don't care why. I'm a law. I don't need to explain why. This is what's going to happen. Laws are not like better theories that have just been tested lots. Okay, that's the big common answer I always get. Oh, scientific laws have been tested over and over, and they're 100% true, and they're always right. And theories are just educated guesses that just haven't been tested enough yet. No, 100% wrong. Scientific laws tell you what's going to happen, no explanation. Scientific theories are very well tested and explain why something is happening. So one last time here. Laws describe observed patterns in nature without attempting to explain it. Theories explain why things happen. That's it. Okay, moving on. Last part. Why are scientific models useful, and why do we use them? So first off, let's understand what a model is. So a model is basically a representation of an object or an event. It can be a physical representation, or it can be a concept. Okay, so what I mean by that is models can take the physical shape of things, like a globe, or a street map, or the model of a car or something. But I could also draw you a picture and you go, well, this is also what it looks like. And now this picture that I drew, although I put it on paper and it's physical on paper, it's really just an idea that was in my head. So not all models are physical. Okay, some can just be concepts. A concept is an idea that you have come up with. But the main reason we use models is that they make things easier to understand because they're used to observe things that may be too difficult to observe directly. So for example, I can't observe a building that's in my head unless I physically build it and go, oh, that's what it looks like. but it takes lots of money and time to build a building. So I'm not going to do it until I actually know it's going to be a good thing to build. So maybe I'll make instead a small physical replica of the building so I can look at it and go, oh, yeah, that looks pretty good. Yeah, it's about the right size. And ooh, I really like the way that this architecture, blah, blah, blah. So I'm going to make a model. Or I'm going to draw it out on paper so I can now see it with my eyes rather than just thinking about it in my head. Okay? So models are just primarily used to make things easier for us to visualize because it might be too difficult for us to visualize or observe them directly because they don't exist. If data show that a model is wrong, then we either have to change it or replace it with a new model. So, models and information science is constantly being updated, and that's just, a common thing. So if we have a model that maybe works for one thing, but then we learn new information later, and that model doesn't work so well anymore, we just got to throw it away and make a new one. Okay? Science works a lot by making mistakes, to be honest. Most of the discoveries that have ever been discovered in science history is because someone actually messed up. It's not because they were actually really smart and they just figured it out. A lot of times they were doing something and then something happened and they didn't realize, like, oh, that's not what I meant to do. They look at it and go, but that's better. And then all of a sudden they learn information that they were never trying to get in the first place. Okay? Very common. Very, very, very common. So newer models are constantly replacing old models, and that's just a sign that new discoveries are continually happening, right? That's part of doing science. So, all right. Anyway, I know these notes were a bit longer than the first section, but thanks for sticking with me. I hope you learned something here. As always, if you have questions, feel free to reach out to me either email or in person or Google Meet or something or other. But So I'm Mr. Bosquez. Again, thanks for watching, and I'll see you in the next one. Bye.